Okay, so here we go with our lifting problem. This is another work problem. Here we're going to be using an integral to figure out how much work it takes to hoist this. You can see here I've gotten this bag of sand drawn. It's 150 pounds, as you can see, and that's, yes, that is my best attempt to draw a bag of sand. We're going to hoist this thing 50 feet up to the top of a building or something. That's not the point. The point is we need to figure out how much work it's going to take to do this. And we're going to use an integral for this. But we have to change perspective on this a little bit. In the previous video, we were doing pumping problems. So we kind of stopped at a particular point in the tank. We were integrating from the bottom to the top, and we sliced it, and we found sort of this slice of water, which would have a particular volume. It had an infinitesimal height and some area that depended on where you sliced it. And we thought of, the work it would take to lift each one of these slices up to the top. Here, we can't really think of anything to slice. We're sort of at a loss, because how do you take cross sections? It's this thing which is being hoisted upwards, but there's no, it doesn't seem like there's a way to slice it. But there is, and this is the cool thing, is that again we need to think of this as our integral, our sum, as adding up infinitesimals of work. So I'm just putting this work times dw. I'll call this the infinitesimal in work. And we're going to try to think, so how can we figure out at any particular point between the ground and the top of this thing, how much work is being done at that point? Even though we can't visualize it in terms of these slices and cross sections, we're going to think about it in the same way. And how are we going to do that? Let's go down. Actually, let me get rid of this first, because I want to come back up and do. That's not actually the work. How we're going to build the integral. We do need to remember that work. I probably should have written this out at the beginning, so it'd be nicer. Work is equal to weight. I'm going to do weight times distance. So the weight of the thing that you have to lift times how far you have to lift it. Now we see that this bag of sand is 150 pounds. So if I wanted to lift it 50 feet, I would just multiply 50 times 150, and that would be my 7,500 foot-pounds, something like that. But there's this sort of added dimension, which is why we need an integral for this. Sand is leaking out of the bag, and it's leaking out of the bag at a rate of 0.75 pounds per foot. And so we're going to have to take that into account. And that's why, because as this thing goes up, the weight is changing. That's why we're going to need an integral for it. So just the same way that the volume of water in a slice was changing as we moved up that tank, now and hence the amount of work that had to be done was changing. Now the weight of this thing is changing. So we're gonna have an integral which is going to have to take into account the weight. So our weight, and then it's going to be from 0 to 50, But then there's going to be, because we're going in the vertical direction, there's going to be this dy in here. And the key to understanding this one, because it's definitely a shift in perspective, is what does the dy represent? In the previous one, the dy represented the kind of the width. Here, the dy is going to represent, it was the width of the cross section, or the infinitesimal height of the cross section. Here, the dy is going to represent something completely different. And this is the kind of conceptual twist that sort of trips most people up. So let's just come down here, where we have this diagram. As I said in the last video, no matter what we're doing with integrals, it's going to involve slicing. We're going to be slicing and taking cross sections. And so when in doubt with an integral, draw a typical slice and see what this slice represents. Now, this, I probably should have copied the picture over from here, but from the last one, but I'm just going to keep referring to it because I really want to stress the parallels. And in the last one, we had these slices, and at any point we stopped. So this will be like a point y coming up from the ground. if this were the pumping problem, we'd think, okay, how high, how far am I going to have to lift or pump this cross-sectional thingy, right? And that ended up being, it was 5 minus y, because we had to get the thing out of a spout, which was 5 feet off the ground. And then we multiplied by, it was like an 8y, which was the area of the thing, and the dy was the height. And then we integrated, I think, from 0 to 3, definitely not from 0 to 5. That's what we did in the last one. Here, it's a little bit different. Here, when I take these cross-sections, I have to think, what does this represent? It's just, this is empty air that I'm cutting. So what is the point of this thing, that this cross-sectional thing, this slice that I'm going to add up? Well, I mentioned the last one, that what we're always doing with integrals is taking an infinite sum, or at least this is how we're thinking of it, taking an infinite sum of infinitesimal objects. And I said objects specifically because I wanted to kind of leave it open what they could be. In the case of areas, area integrals, it was these infinitesimally thin line segments. That was the object. In the case of volumes, the objects were these shells or washers with this infinitesimal width. In the case of pumping, it was an infinitesimally high slice of water, so it had some volume. But it actually wasn't. The infinitesimal quantity in the pumping video was actually the work. We were taking infinitesimal quantities of work and adding them all up. The volume was only one component of the work. So to write this thing again, it was 0 to 3, and we had, I think it was 6.25 times, it was, 5 minus y times 8y dy. And I said that the infinitesimal thing we're adding up is actually all of this stuff. So this was the volume, this thing here, this 8y dy, that was the volume. And then I saw how far I have to lift it and also how much it weighs. I multiplied by the 6.25, the weight of water. This thing here was in cubic feet, and then this was the weight per cubic foot. And so the point is that if I rewrite this yet again and make this 0 to 3, now 6.25 times 5 minus y times 8y dy, now I can see that this represents an infinitesimal quantity of work that's required to do. The infinitesimal volume times the weight per volume times the distance that particular infinitesimal volume has to be lifted, or an infinitesimal amount of weight has to be lifted. That gives me the infinitesimal increment of work, and I'm summing them from 0 to 3. And so here we're going to be doing the same thing, except we just can't visualize it quite as much, but I can slice it not into bits of volume, but into bits of work. And that's what this thing here represents. I'm thinking, so immediately I see that my bounds of integration have to be from 0 to 50. That's where y is going from. And I know that at a particular point y, I'm lifting this thing which has this changing weight. The weight of this thing is changing. It starts at being 150, and then the sand starts leaking out of it. Every time I raise it a foot, the sand is leaking, we're assuming continuously, so we can do this at a rate of 0.75 pounds per foot. I'm going to be stopping again, slicing at some point y, and saying, all right, here, what is the amount of work that's being done? How much work is being done at that point? I'm going to consider this thing, this purple, whoa, I don't want to do that. This purple bar thing here, this purple slice, that is my infinitesimal unit of work. And I'm adding up all of them from 0 to 50. But I'm not thinking of it like with the area integral, like it's sweeping out. I'm actually sort of just thinking, as I go up, at each point, some work is being done. And I want to add up all those bits of work. And how much work is being done? Well, at this point y, I need to know how much the thing weighs, and that's not that hard to find. So it started out weighing 150 pounds, and then I lose 0.75 pounds of sand per foot. So I'm subtracting 3 over 4 times y, because at this point I've picked y. It's been moved up by y feet, so it's lost 3 over 4 pounds, 3 over 4 times y, pounds of sand. But now I'm thinking, okay, am I going to multiply by what is this, 50? I can do it better than that. Is this 50 minus y? That's a little bit better, not much. Because you would kind of think, well, does this slice here need to be moved up 50 minus y feet now? And this is where it gets conceptually weird and people get a little bit confused, because obviously, no, there's no slice here. I know at that point what the weight is. So what do I do? What do I put in? What does this dy represent? Before, and this is the whole key to this thing, what does the dy represent? In the previous one, the dy was the infinitesimal height. In the area one, it was an infinitesimal width. In the volumes one, it was an infinitesimal width. Here, what does it represent? And this is the key to the whole thing. It represents an infinitesimal distance. I'm thinking of this, every point on this thing. At a point y, I'm thinking of stopping there, thinking, all right, at this point y, how much does the thing weigh? What is the weight of the thing? And the weight is going to be 150 minus 3 over 4y. And now I think, okay, at this point, it has this particular weight, and I'm lifting it by an infinitesimal amount, dy. And this is what allows me to compute the work. I can think of this as at every point, stopping, figuring out how much does this thing weigh at this particular point. It's going to have a weight, and I should put this little dotted line in to represent the actual height y. So that's my y. And then I think, all right, I can figure out what the y is, 150 minus 3 over 4y. And then I think of moving this thing up by an infinitesimally small amount, dy. And then I do that again and again and again, and that's what the integral is. The integral is taking the infinite sum, as I go from 0 to 50, of the actual weight at that particular point, just like I had the actual height of the function when I was doing the area integral. But then instead of multiplying it by an infinitesimal width, I'm lifting it by this infinitesimal amount, dy. And that is the idea behind this. That's kind of what's going on with this thing. So, and I think this is kind of the sticking point. My whole goal in these videos, and every time I teach, is to kind of identify the thing that people are going to get stuck on, the sticking point that's going to stop you from understanding these things, or it's going to lead to a misunderstanding, which will screw you up. And generally the way that I do this is just kind of think, what did I get stuck on when I was doing this? And it turns out my mistakes tend to be actually pretty common. So let's go back up here to this thing. We are going to end up with this this integral, now that we understand that the dy, of course, is infinitesimal height, adding up all of these particular weights at a point, adding them up, lifting them infinitesimal amounts, and then adding up all those infinitesimal bits of work. And again, we're thinking of this as infinitesimal bits of work times this like dw or whatever. Don't read too much into this. This is just kind of to remind you that what we are adding up is units of work. At the end of the day, this is how we came up with what that work is. The dy had a different role, but it is adding up bits of work. So our final integral is going to be integral from 0 to 50 of 150 minus 3 over 4y times dy. And you can compute this. By the way, I'm not actually computing any of these integrals because these are just polynomials. They're very easy to anti-differentiate. But and I want you guys to be focused on the concept here and not sort of get distracted with the computations. I think it's really important to sort of let the idea sink in rather than worry about a bunch of computations immediately. So for the sort of second part of this, and I'll do this a bit later, exercise is compute this or set up at least the same integral. But now we're going to think, before you may have noticed, we were assuming that the weight of the rope that we were using to pull this thing up didn't matter, that it was negligible. That's a common assumption in these things, right? The heavier the thing gets, the less the rope tends to matter. But suppose now we know that the rope weighs 1.5 pounds per foot. The rope is 1.5 pounds per foot. So now the weight of the rope is also going to be changing. As we lift this thing, as we hoist it, sand is leaking out, and also there's less rope that needs to be lifted. So see if you can go ahead and using the same approach, the same kind of slicing method, and it really is a good idea to actually stop and draw the picture every time you do this. Every time you do anything in math, try to draw a picture that corresponds to it, that helps you understand what's going on in some way. So see if you can draw the picture and set up the integral and come up with an integral which will give you the total work required to hoist the thing, assuming that now, in addition to the sand leaking out at 0.75 pounds per foot, also the rope weighs 1.5 pounds per foot. And then we'll do the answer to that in the next video, which maybe we'll post in a day or two.